Okay, so Michael is going to talk about matrix element sums evaluated via differential equations and calculations of atomic molecular properties. And of course, as I pointed out earlier, this is all reminiscent of the Delgano and Lewis method of 56. Michael.
So I'm delighted to have the opportunity to give a talk at this symposium. Let me give a little bit of background first. I was very fortunate in 42 years ago in what Aveen would call AD 38 to embark on a PhD with Alex at the Queen's University of Belfast. Not only was I getting the opportunity to be exposed to the best of scientific method, but it was also the beginning of a long friendship with Alex over 42 years. It's said that the mark of a gentleman is somebody who always has time and interest in other people. And I can certainly say that Alex is one of the scientific gentlemen of the world in that sense. In 1967, Alex moved here, as you know, and he invited me to come and work with him and to finish my PhD here. That, in a sense, was a life-changing experience because for those of us who lived in Northern Ireland in those days, to go across the water, as they say there, to England was a big deal. So to come transatlantic was really quite something. Gordon was reminiscing about the poker club. When I first joined Alexander's ragtime band, as it were, and we had the poker club, I probably had the distinction of being the worst ever of the poker group. Alex may remember that around 1962, which I think would be AD 34, he appeared on Ulster television giving a talk about computers and applied mathematics. And I remember in my last year in school seeing that, and I was very, very interested in it. It struck me that the name Dalgarno was exotic, and at the time I didn't know it was Scottish. So as I live in Scotland now, I thought I would do a little bit of brief investigation before coming. I discovered two things. There's a small group of Dalgarno in the southwest of Scotland, the outlying states. They could be the Rydberg states of the Dalgarnos, but the main ones are in Aberdeen, and that Alex is, of course, from Aberdeen. Further investigation, just using the internet, I discovered that a literary club called the Maitland Club was formed in Glasgow in 1828, AD-100. And one of their interests was in the works of a previous Dalgarno from Aberdeen, who was also a scientist. And he was also concerned very much with other people. And he invented the sign language for the hard of hearing. So it may be that Alex is related in some way to George Dalgarno, who lived in 1650 or thereabouts. George Dalgarno had some correspondence with people like Leibniz, as it happened. But to get back to cut to the chase and get back to the main thrust of the talk. As we know from this meeting, the contributions that Alex has made in science in general is just staggering by anybody's appearance. The areas that we've seen that he has accomplished is atomic and molecular physics, which is what I was studying. The Earth's atmosphere, planetary atmospheres. He just made an enormous contribution in that. And then chemistry of the interstellar medium, a subject which he more or less invented. And as we've seen over the last 2 days, has had an enormous influence and contribution. When I was preparing this talk, I referred to about 55 of Alex's papers, and that is something approximately 5% of his total output. Well, to move to what I'm going to talk about, this is just one aspect of what Alex has done over the years. And for any other person, just to have done this on their own would be a lifetime of scientific achievement. But this is just one small part of what Alex has done altogether. Perturbation theory very often leads to, as we saw from Gordon's talk, to expressions of infinite summations of matrix elements. They can be recast, as Alex realized, in terms of a few terms that depend on the solution of differential equations. In the early days, of course, those differential equations were difficult to solve, and only in a few cases are analytic solutions available, hydrogen and hydrogen-like ions being typical examples. So the way to do it really was to get either a numerical variational method, which is the kinds of things that Gordon was talking about, or some kind of finite step method. And Alex was one of the first people to use a computer to solve these problems. He had used this computer with the great name of Whirlwind at MIT in the 50s. Those were the days when computers were given really good names and not silly names like Apple. So he used the Whirlwind computer and realized that computers were going to become available much more widely. And once computers became available, then the numerical solutions of these equations would become commonplace, fairly easy to do. Well, easy is probably not the right word. The challenge in the early days of computers, of course, was to get it to run long enough before it developed a hardware fault. Nowadays, it's to write a program that doesn't have a fault built into the middle of it somewhere.
Michael, that's the Whirlwind.
Yeah. Oh, sorry, the misprint. The Whirlwind computer. So let's see what this is about. So I'm going to just take a completely trivial example just to show you how the method works. Suppose we want to calculate, just say, the static dipole polarizability. And Gordon was talking, you've seen that equation 3/4 of an hour ago or so. That would be the expression for the dipole polarizability. And in that, we have an infinite sum over matrix elements over the complete set of states that we're looking at. This is with the polarizability of something in the ground state, which I've designated 0, and S are just the excited states. And these are the energies. The S prime indicates that we've got an integration over all the states except the ground state, and including the continuum. This is rather awkward to calculate, of course. That expression tells us what the polarizability is going to look like. And just before continuing, Gordon mentioned the model potential methods, where you try and get a model spectrum of some kind. And that is where you effectively you have a structure that looks like that one, except that you put a finite number of states in, and you have to get some kind of way of calculating what the effective dipole matrix element would be and what the effective energy is. And we've seen that that is a very powerful method. But if you were trying to do this numerically, it's inconvenient. There's an infinite number of terms, so you have to satisfy yourself with a finite number of them. And each of those terms, of course, is very awkward to calculate. Each of those terms has got a big calculation in itself, because you've got to know what the excited state is, and you've got to know what its energy is, and then you've got to do that integral. And of course, what you do about the continuum is not at all obvious. The model spectrum methods of Gordon have got methods of dealing with the continuum. So really, you end up just truncating the sum and doing an inconvenient calculation, and you don't know how accurate it's going to be. The method advocated by Alex, of course, was to say that if we took this differential equation at the bottom, and we solved that differential equation, and calculate this quadrature here, then we've got back the same as we had here. I'm just going to concentrate on the simple early cases of spherical atoms, so that we can take out these terms which deal with orthogonality. So we've got that simple differential equation, and we can solve that on a computer. So that looks great. So have we got something for nothing out of this practical way of calculating it? Well, not quite. Gordon showed that slide in his talk. That's the dynamic dipole polarizability for a frequency nu. And this then is, that is the infinite sum way of doing it. And when we use the method of Alex, we get it reduced just down to this quadrature, and where these functions chi plus or minus nu satisfy these differential equations. So we solve the equations, put it into there, and there it is. So what's the catch? It looks just too easy. Well, there are some catches when you do this, because let's suppose that the excitation frequency was, that the applied frequency was close to exciting the atom into one of the excited states. If we do that, then we'll not have it exactly that, because that's another problem. But if it's close to it, we're going to find that this state is actually very important in the sum. And if that's a high up state, as it were, say a Rydberg state in an atom, it's going to occupy a lot of space. Usually we're reducing these equations into equations where we're just dealing with the radial coordinate. So we have a lot of space to encompass. And if that situation was satisfied, and we integrated our differential equation out, say, typically for an atom, to 5 or 6 atomic units, but this state was actually occupying space, say, out to, say, 20 atomic units, then the method, of course, will not give an accurate answer. So you don't totally get something for nothing. If this is going to excite one of these states, you've got to make sure that the range of integration that you use is enough to hold that state, because you are representing it with this sum. Also, the finite step solutions become slightly difficult if you're close to one of these resonances. And for an atom, the situation is slightly worse, because if you're high up in the Rydberg states, if it's close to that one, it's going to be close to a lot of the other ones as well, because all the states are close together at that stage. So you don't get something for nothing, but it's just a superbly good method of calculating something like this, as long as you're careful. Alex then, with Lewis, formulated some sum rules which became famous, which are famous. Just to see how they work, if we take the second order energy for some perturbation V, we get that expression there. And what I've done there is simply to move the summation over the things that depend on S into the middle. And when you look at that, you can see that this middle bit then is just the projector of that resolvent, or 1 over H minus E0, onto this set of states. And because we've taken out the ground state, it's the ones that are orthogonal to that. So when you do that, when you take this out, you can see that that expression there is the same as this one, where it is satisfying a differential equation. We've just really done that for the polarizability, where the perturbation was the dipole moment. Of course, one might argue it's a bit of a tautology, because possibly the way you got this in the first place was to see this differential equation. But to evaluate this, the best thing to do is to go to the differential equation. Delgano and Lewis paper, which is famous, was concerned with calculating long-range interactions. And one of the things that they found useful to do was to express this first-order perturbed function as a product of the ground state and something else. And it's the something else that you have to know. So if you know that chi is the product of the ground state and something else, then you can go back and put it into that quadrature. You've got to be a little bit careful, of course, because the something else part has a risk of having poles at the point where the ground state is 0, so the product is 0. So when you put that into this expression, you end up with this more general rule. And there is a typo in that, which I'll come to in a minute. You take some arbitrary function, g, and you're trying to calculate that infinite summation, and you find that it can be written just as these quadratures on the right-hand side, where the function f satisfies a differential equation. And the typo is that g there should be an f. So that is the famous sum rule of Dalgarno and Lewis, which has got numerous applications, which I may or may not have time to just mention briefly. Two more sum rules which were useful, and also done by Delgano and Lewis, and then by Dalgarno and Stuart, were this one. They just turn out to be useful in evaluating things like long-range forces. And the Dalgarno and Stuart paper, where they had written down the expression for the first-order correction to a diagonal matrix element. L will be some operator, very often a one-electron operator, and you want to find out that if a perturbation is added to the system, how does that L change? And they showed that it changes to this expression, where once again you need to solve a differential equation. Otherwise, that thing is going to be an infinite sum. So we come to a couple of applications following. I'll just quickly list them rather than describe them, because I don't think there's enough time to describe them. Early papers, and a lot of these were actually done in Belfast, on long-range forces by Delgano, Lewis, and Lynn. And we'll see at the end that these long-range force calculations are still being done now. These were all being done in the 50s. Polarizabilities were done by Dalgarno, Chan, Parkinson, etc., George Victor. The Thomas Kuhn sum rule, which Alex was able to prove, almost falls automatically out of the differential equation formalism. Properties of something like H2 plus with Dalgarno and Stuart, they were calculating things like magnetic susceptibilities, diamagnetic susceptibilities, all one electron operators, going back to just using that equation there. So this is just a list, and that's a short list of the things that where the applications have been made. We'll come on to the next place where this kind of formalism was used, and that is Arterial Fox Theory. There are basically, as I see it, three problems which Alex addressed. The first problem is where you're trying to solve the Hartree-Fock equations themselves, and you know that there's a closely related problem that you do know the answer to. That's to say, you have a Hamiltonian which you can solve, but it's not the Hartree-Fock Hamiltonian. So what you're actually doing then is to treat the perturbation as the difference between the Hartree-Fock approximation and some solvable problem. And then you come back to calculating, say, something like the dipole polarizability, which, coming back to calculating some diagonal property, and then you just need to go back and use that equation there. The second kind of Hartree-Fock problem is where you're actually trying to solve the Hartree-Fock problems themselves, and you ask, how can I actually get a better answer than that? How can I deal with correlation, which is essentially the difference between the Hartree-Fock answer and the real answer? And in that case, you try to solve the Hartree-Fock equations, and that, of course, has become more and more possible with more and more powerful computers, even in the 60s when this was being started. And in that case, the perturbation that you're dealing with is the difference between the real problem and the Hartree-Fock problem. And once again, you just go back to the correct the diagonal matrix elements in this way. Alex with Morris Cohen, who is here, also proved that if you have the exact Hartree-Fock problem, that the diagonal corrections are actually zero. And that was a very important result. The third Hartree-Fock problem is where you turn on an external perturbation, which could be time varying or fixed, an electric field, and then you go ahead and calculate the polarizabilities. The problem that I looked at for my PhD, that Alex had suggested to me, was to look at the time-dependent Hartree-Fock equations. These have a kind of magic property, because when you solve them, you discover that what you've solved, say the dipole polarizability, has automatically got the correlation built in to first order. It's equivalent to the random phase approximation, something which had been shown in some cases, and something which I also proved in my thesis. So I'd done some work. George Victor had done a lot of work on this, and then these people, Alex, and then this group, Hurst, Kavish, and Kavishwar, had done a lot of work on shielding factors. Shielding factors is where you're allowing for the change in an external electric field due to the polarizability of the atom that is being applied to. These were then extended by Debbie Watson, I think, who's here, to look at a molecular version. What I was looking at was very simple, just helium, and Debbie Watson, and I think that this is a different Stuart, I think it's Ron Stuart. They extended that to a molecular version, and then Walter Johnson and others extended it to a relativistic version. the Harvard-Fock equations look like this, so the time-dependent ones. So they're like the ones that were shown earlier for the polarizability, except that they've got this extra coupling term in. But they're a set of solvable problems. A couple of things that I've been involved in visiting Alex over the years was a pre-dissociation calculation, where we had shown that the Delgano and Lewis method can be used to simplify the expression for the shift. The pre-dissociation is effectively the interaction between a continuum state which is degenerate with a bound state of a molecule. It turns out that the Schumann-Runge bands of O2 had been looked at very extensively at CFA by an experimental group, which was basically Bill Parkinson and Yoshino and Alan Chung visiting and others. And they had a great deal of data on the Schumann-Runge bands. We were able to use this theory to analyze that data and explain it, basically to try and find interaction potentials. The other problem that I had looked at recently was with these other authors, and this was really developed by Marinescu and Alex and Hussein, was to look at Raman and Rayleigh scattering. In these cases, you get something called the Goppert-Mayer expression that describes, for example, the Raman scattering. And that is an infinite, again, one of these infinite sums, which can be reduced to something manageable by solving perturbed differential equations. And we looked at differential equations like this. One of the twists there is that when you come close to one of the Schumann-Runge resonances, that these things become difficult to solve. And we put in a width into the negative frequency version of it, so that when h nu coincided with one of the excitation Schumann-Runge frequencies, then this thing wouldn't explode. And we were able to use for these widths the data which had originally come from this experimental work at the CFA. At the moment, of course, you know that there's just an explosion of interest in low-temperature physics. And low-temperature physics, the low-temperature collisions, is extremely sensitive to knowledge of, for example, what the long-range interaction between atoms and molecules would be. And this theory is being, as we speak, more or less being developed by Alex and collaborators. What they're doing is to calculate things like the leading order van der Waals term and the others, say C6, with relativistic effects. And essentially it comes down to solving really what you need to know is what the polarizability is at an imaginary frequency. Two approaches to do that are: one is to use Gordon-Drake's approach of getting the model spectrum and then putting an imaginary frequency into it. The other way is to go back to the differential equations like this, and you simply write that then as a pair of equations for real and imaginary components of the response, and that is what is being used in all of this. So I conclude this talk by saying that this was a method which was developed by Alex 50 years ago. It's been applied to many systems by very many authors, and probably many who don't know Alex personally, but would have seen it, all of this stuff in the literature. So it's been used, and the applications have gone from the earliest studies of very simple atoms right up to much more complicated systems now. The systems being looked at now, I mean, if you thought back to the 50s, would just be unbelievable that you could do this. This method will continue to be used. As Aveen said, the true legacy of Alex is whether the methods will continue. They're not just methods that are being developed, done, and that's it. These methods, the legacy, and just in this one topic, is that these methods are still being used and will continue to be used. I'll come back to that slide just in a moment, but just to give you some idea of the enormity of Alex's output, And as I said, this is something like 5% of it. Here are just a few slides of showing just a few references. So there's about 55 references there. That's just a fraction of the work that he has done. So I'd like to thank Alex for many years, 42 years of friendship and interesting collaborations, and the opportunity to visit here often. I probably regard this as a kind of second home. I also would like to thank the organizers of the conference for the invitation to speak. It's an honor to speak at this because, as you can see, there's not that many talks in the program altogether, and there's many people who would have liked to do it, so I'm very pleased that I was asked to do it. So I'd like to finish then by saying that, as I say in the football terraces back in Britain, there is only one Alex Dalgarno. Thank you.
Well done, Michael. That was a truly extremely interesting talk, which really does show one good idea just can be expanded all over the place. Now, I noticed, Derek, I haven't heard from you, Derek, for so long. I've got...
John Lewis was, of course, brains and Lewis, photons in H minus 1955. The thing is that Delgano and Lewis had quite a fortuitous incipience. John Lewis came up one year from Dublin Institute of Advanced Studies. By the way, he lectured to me at Oxford. He had been at RBAI like David Bates, and he recounted the following amusing tale. Bates called him in. No doubt he was drumming the desk with his paper knife, and he said, "Well now, young man, I want you to do second-born calculations, and if you work 40 hours a week, you will have so many calculations done, and then it'll take you about a year." So John Lewis went away, thought about it, came back and said, "Sorry, David, I don't think I really would like to do that." "In that case, young man, you will have to work with Alex Dalgarno." What a privilege.
Well done, Derek. Thank you. Okay, well, who could follow up with that?
I can
it's
make
a hard act to follow.
Ray, I'll make another comment there. I didn't realize that you said John Lewis was at RBAI. That's just for those who don't know Belfast. That's a famous school in Belfast, and the reason I mention it is because I also was there. But I understand that David Bates. We'll come back to that. But I understand David Bates was there and didn't actually enjoy it as much as maybe some of the rest of us, because he didn't like rugby, I think.
That's right.
I didn't enjoy rugby either at Inst.
Right.
I just had to put up with it.
That's right. The headmaster there, Michael, was putting rugby and football
ahead of...
David just was completely unhappy there, and he left.
But as it turns out, of Instonians, as people who go to this place, it's called the Royal Belfast Institution, academical institution. And Instonians, as it was called, David Bates is probably one of the most famous of Instonians. I think Lord Kelvin also went to the school for 9 months, and the school claimed him as one of their own.